So this video tutorial is on modal analysis of a cantilever beam. So the problem is like this. It's a cantilever beam. So this is a cantilever beam. So length of the beam is 1 meter and cross section is 0.01 meter into 0.01 meter. So density is given, it is 7830 kg per meter cube, and modulus of elasticity, it is 2 into 10 to the power of 11 Newton per meter square. So objective of the modal analysis is to extract the natural frequency of the member and corresponding mode shapes. So theoretical solution is this. So this is a theoretical solution. So there are 5 natural frequencies are here. So 8.3 hertz, 51.94 hertz. So these are the theoretical solutions. There are 5 natural frequencies. There will be many natural frequencies. Here we extract, here I am showing 5 natural frequencies. So these are the natural frequencies, first 5 natural frequencies. When the member is excited, if the excitation frequency, if it matches with this first natural frequency, how it behaves. Then second natural frequency, the behavior. So those, the shape, when it excited to a particular natural frequency, the shape of vibration, that we call it as mode shape. So here we use this term mode shape. So natural frequency are these things, and behavior of the member at respective natural frequencies, that we call it as mode shapes. So how to solve this problem in ANSYS, that I'm going to explain here. First you change the job name. And set the working directory also. Check for the working directory. So preferences, select structural analysis. Okay. Preprocessor, element type, add. So here this member is 2D member. Okay. So cantilever beam is 2D member. So but the member available in this version here, it is 3D. Okay. So 3D. So we will constrain this for 2D boundary condition, and then we will solve. So I'll select this option beam. Under beam it is 2 node 188 element. Say OK, close. I selected this element and close, right. So real constant is not required here, because we will be assigning the section detail in this option here, section. Before going to that, material properties, material models. So here the material is steel. It is 2e to the power of 11. Poisson's ratio is 0.3. So modulus of elasticity and Poisson's ratio. Density is required. If the density value is not entered, it will not give any result. Okay, it will not solve the problem. You will not get any result. So this is very important property. Without this, it will not solve for modal analysis. 7830 kg per meter cube. Okay, right. So meter property is assigned. So now I will create the section. I'll assign the section, sorry. Assign the section. It is beam common section. I will just give a name for this, A. So breadth is 0.01 meter and height is also 0.01 meter. These values I will give 12 and this also 12. So the section properties are like this. Okay. Section is assigned. Now I'll create the model. Modeling, create key points in active coordinate system. First key point at origin 0. Second key point at 1 meter, at a distance of 1 meter. Here I am taking all the dimensions in a meter. Okay. I'm maintaining the unit meter. So line, straight line. I'll connect these two key points. Okay. Then meshing. So geometrical model is created. I'll go for meshing, mesh tool. Elements, I will set number of element divisions 50. Okay. So mesh this member. So it is meshed. I will check for this view, 3D view. So it is meshed like this. Right. The 12 and 12 value what I given, that is here like this. Okay. So 12 divisions and 12 divisions. I will disable this view. It is like this. So now I will apply boundary condition. So load, it is cantilever beam. So one end is fixed. Displacement on key point. On this key point, it is all degrees of freedom. And then since this is a 3D element, I need to restrict the movement so that uh, uh, so that it resembles a 2D element. I need to give these boundary conditions also. So displacement on nodes, I'll pick all the nodes and it is UZ, rotation about X, rotation about Y. So select these three and say OK, right. So this is the boundary condition. Now it is a plane, it can move in only one plane. So after this, so don't apply any load here. We are not applying any load on this, just boundary condition. And remember, you need to assign the material properties, density material property, otherwise it will not show any result. Okay. So load is not required. We don't apply any load. Boundary condition we apply. And then go to solution, analysis type. Analysis type, new analysis, modal, say OK. Analysis options, select this block length source. Modes to extract, I'll say 5 modes to extract. Modes to expand is also 5. Say OK. Okay, so this you need not to enter, just say OK. After this, solve. So it is solved, solution is done. The results we can see here. Results, general processor, result summary. You can see the natural frequencies extracted here. And so this is the natural frequency here. Okay, right. So it is first one, it is 8.311. Here it is 8.16. Second one is 51.18. It is 51.94. Third one is 143 here, and the actual value is 145. 281 and 285 and 466 and 433. So these values you uh, should compare with this theoretical value and add one more column here. So column is ANSYS result and one more column which is for error. So this is the procedure to get the natural frequencies. So now mode shapes. So when it is excited to this first natural frequency, how the member behaves. That is mode shape of first natural frequency. So how to do that? So it is like this. Read results first set. First set means it will read the first natural frequencies. Go to plot controls, animate, mode shape, degree of freedom solution, deformed plus undeformed. Say OK. So it moves like this. So this is the behavior of the member when it is excited to a frequency which matches first natural frequency. In this case, it is 8.13. So when it is excited to 8.13 hertz, then the member behaves like this. So this is the mode shape. So you need to plot this shape. So up maximum moments, you can just write the sketch showing the uh, uppermost and lowermost position of the member. You can show in a sketch, and that will be the mode shape. So this is the first mode. Now second mode, I'll say next set. Okay, so this will be for second natural frequency. Just click only once. Okay, so then it will go for the next. Plot controls, animate, mode shape. Okay, so this is the second mode. Second mode shape. So that means when the member is excited to the second natural frequency, it behaves like this. Similarly, third natural frequencies. So this is the third mode. You need to make it like this. Write this position and another extreme position. So this is a mode shape. Third mode. Similarly, fourth mode. Fourth mode is like this. You need to plot these shapes with respect to corresponding natural frequencies. So this is the fourth mode for fourth natural frequency. Next set, plot controls, animate, mode shape. This is the fifth mode. Okay, so you need to write these mode shapes. Yes, so this is the uh, procedure for modal analysis of cantilever beam, extracting natural frequencies and respective mode shapes.